Hey everybody, this is probably our next to last video. We're going to be talking about something called periodic trends. So I'm sure you've heard the word trend before, and a trend is something, of course, it changes in a predictable way. And if we're talking about a periodic trend, we're talking about something that changes in a predictable way as you go, one way or other across a period or up or down a group. So here's a good example that's probably easy to kind of see. Take a look. Let me draw in a metalloid line. Okay, remember the metalloids? So take a look down this group right here. Nitrogen is a nonmetal. Phosphorus is a nonmetal. Arsenic is a metalloid. Antimony is a metalloid. Bismuth is a metal, a full-on metal. So as we went down this group, things got more and more metallic. We went from a nonmetal to a metalloid, which has some metallic character, to a full-on metal. And so I think we would see that trend in some other groups as well. So metallic character increases down a group. Looking across a period, like let's look across this period for instance. Sodium is a metal, magnesium is a metal, aluminum is a metal, but silicon, you probably can't even see that anymore. Let me erase that. Silicon is a metalloid. Phosphorus is a nonmetal. Sulfur is a nonmetal. Chlorine is a nonmetal. Argon is a nonmetal. So as we go across, metallic character gets less. Or you could think about it the other way. If we go this way, metallic character increases. So that's an example of a periodic trend. But we're going to be talking about three periodic trends that are a little more subtle than this. In this video, we'll be talking about the first two. Atomic radius, which is basically the size of the atom, and electronegativity, which is how badly an atom wants to gain electrons. Ionization energy we'll cover in our last video. So atomic radius is the first periodic trend we'll talk about. Atomic radius is basically how big the atom is. It's the size of the atom. So we measure it from the nucleus to the outermost electron. And so you can imagine then, if it's measured from the nucleus to the valence electrons, that how many energy levels you have plays a big part in the radius. And so, like looking at this atom, it's only got two energy levels. So let's say the outermost electron is here, then, there's your radius. Here we have an additional energy level, so that means the radius is bigger. Here we have another additional energy level, so the radius is even bigger there. So the more energy levels, the bigger the atom. That makes sense. Something that's a little less obvious, though, is that the nuclear charge increases. As you add protons to the nucleus, the charge increases. 3 protons is plus 3, 4 protons is plus 4, 5 protons is plus 5. That increased nuclear charge is going to pull electrons in more tightly. And so the number of protons in a nucleus also plays a role in this. Okay, so atomic radius increases as you go down a group of elements on the periodic table. That happens for two reasons. Reason one, energy, like we just spoke about, energy levels are added to the atom, and that increases the distance from the nucleus to the outermost electron. And then the second thing is something called the shielding effect. So let's take a closer look. Okay, so as we go down a group, atomic radius increases. So here's the alkali metals. Lithium, sodium, potassium, rubidium, cesium, and francium. I do the first four. So take a look at lithium. Lithium has 3 electrons, so its configuration is 1s2, 2s1. So here's kind of what it would look like with 3 protons in the nucleus. That's where the plus 3 comes from. And then the 1s2 is the green, and then the second energy level is the red one. Okay, so that's the 2s1. Over here, the number of protons in the nucleus increases, but we add an outer energy level. Okay, so you can see we got 3 rings around the nucleus, so that outer electron configuration is 3s1. So see what we've got going on here? Lithium's outer electron configuration is 2s1. Sodium's is 3s1. As you can see here with potassium, its outer electron configuration is 4s1, 5s1 for rubidium. So as we go down this group, we keep on adding an energy level. Now there's only one electron in it, but that makes the atom bigger. Now I did note that the number of protons in the nucleus increases, and so that's going to pull the electrons in more tightly, but there is something that kind of cancels that to some degree. But the lesson we learned from this slide is this. As you go down a group, the number of energy levels increases, as we can plainly see, and that causes the radius to get bigger. Okay, so besides the fact that as you go down a group, energy levels are being added, that's one thing that causes the radius to increase. There's another thing that causes the radius to increase. As we go down this group, the number of energy levels, as you can see, gets bigger and bigger. The nuclear charge also increases, but like I was saying, that's partially mitigated by the fact that look at all these energy levels that are between the nucleus and the outer electron. Here, take a look at this big one I drew. So here's the nucleus, here's the outermost electron. There are 1, 2, 3, 4 energy levels between the nucleus and the outermost electron. All those inner energy levels prevent the nucleus from holding on to the electron as tightly as it could. As a result, this outer electron kind of drifts farther away, and as a result, that also helps the radius get bigger. So the shielding effect occurs when the inner energy levels shield the attraction that the nucleus has for the outer electrons, and they don't hold on to them as tightly. Okay, so let's look at a situation where the atomic radius gets smaller as we move across a group. So I wrote these electron configurations for the as we move across a period. So looking at the second period, we got lithium at 1s2, 2s1. So its outer electron is in the second energy level. Beryllium adds an electron, 1s2, 2s2. Boron adds an electron, 2s2, 2p1. Carbon adds another electron, 1s2, 2s2, 2p2. Nitrogen, 2p3. Oxygen, 2p4. The point I'm trying to make is this. Electrons are being added as we go across this group, but they're being added to the same energy level all the way across. So it's not like we're adding full energy levels. We're adding electrons, but they're going into the same energy level, the second. So, you might assume then, okay, well, the atom doesn't get any bigger going across since we're not adding energy levels. Well, something else does change though. If we look here, we can see how the nuclear charge increases, all right? Lithium has 3 protons in the nucleus. Beryllium has 4 protons. Boron has 5 protons, and so on. That increased nuclear charge pulls electrons in more tightly, and as I've tried to illustrate here, you can see that the radius shrinks. Another way to say it is it gets bigger going this way. But the reason that the radius gets smaller is because electrons are added to the same energy level. So they don't get farther away, but the nuclear charge increases and that pulls them in more tightly. Tell me about the shielding effect here. I mean, what part does it play? Well, as you can see, we don't add energy levels, so the shielding effect stays the same all the way across, so it's not really a factor. Okay, so to sum up, atomic radius decreases across a period for 2 reasons. One, electrons are being added across a period, but they're being added to the same energy level. Now that alone won't explain it, because if they're being added to the same energy level, it sounds like they won't get any bigger, they'll stay the same. But this also occurs. The number of protons added to the nucleus increases as you go across the period, and that pulls the electrons in more tightly, and that causes the atom to get smaller. So this little schematic here that shows actual atomic radii in picometers can kind of shed some light on things. As you can see, as you go down a group, sure enough, atomic radius increases. As we add energy levels, the atom gets bigger, but it's also because of the shielding effect. Now, as we go across this way, the atomic radius gets smaller, but another way to look at it is back the other way, they get bigger. I like looking at it this way because it's a clear indication that the atoms in this corner of the periodic table are bigger than the atoms in this corner of the periodic table. So that's the trend for atomic radius, going down a group and across a period. The second and the last one we'll talk about in this video, periodic trend, is something called electronegativity. So what is that? It's the attraction an atom has for electrons, how badly an atom wants to gain electrons. So the greater the electronegativity an atom has, the better it is as gaining an electron. And when it does that, it gains a negative charge and becomes an anion in the process. Okay, so let's have a little chat here about electronegativity. Here's the noble gases. Remember, the noble gases are very unreactive. Why is that? It's because they are very stable. They all have 8 electrons in the outer energy level, well, except for helium, which has 2 in the first, but that's full. So that makes them really stable. All the other elements want to have the same kind of electron arrangement as the noble gases. So look at these halogens right here. Fluorine is 1 electron away from having the same configuration as neon. Chlorine is 1 electron away from having the same configuration as argon. Same thing down the rest of the group. So what that means is, does fluorine want to gain an electron? Yeah. If it gains 1, then it becomes really stable. Does chlorine want to gain an electron? You betcha. Then it has the same configuration as argon and it's really stable. Same way down the rest of the group. So these halogens here are very electronegative. They really, really want to gain electrons. Let's take a look at the other end of that spectrum. Take a look at the alkali metals, group 1. These guys also want to be a noble gas, but take a look at sodium. It has 11 electrons. So it has 2 choices to become like a noble gas, electron-wise. It can gain 7 to be like argon, or it can lose 1 to be like neon. Of course, losing 1 is what it does. That's why these are all +1. But what that means is, do you think sodium wants to gain an electron? No way. It wants to lose electrons so it can have a noble gas configuration. So these guys are very not electronegative. They do not want to gain electrons. So here's the deal. Electronegativity increases going across a period, so as we go left to right, it gets bigger, and it decreases, that should say down a group, and it decreases down a group. Well, if it decreases down a group, it increases up a group. So why does electronegativity increase across a period? Well, remember we were talking about atomic radius with going across a period, and we know that the number of protons increase in the nucleus. That causes the nuclear charge to increase. That means that the nucleus holds on to its electrons more tightly, and it does a better job at attracting other electrons. But if we go down a group, we keep adding energy levels. Remember the shielding effect? And so the atom can't even hold on to its own electrons very well, much less attract others. So electronegativity increases across a period, but it decreases down a group. So then you could say the electronegativity increases this direction, and since it decreases down, it increases going up. So the most electronegative elements are right here. Actually, fluorine is the most electronegative element. These guys, they do not want to gain electrons, so they are the least electronegative. Most electronegative, least. Notice the correlation between that and atomic radius. The smallest atoms, which are up here, want to gain electrons the most. The bigger atoms want to gain electrons the least. Thanks for watching.